This lesson will go over electron configuration and orbital filling diagrams. So first, what is electron configuration? What is its purpose? So an electron configuration determines an electron's location. So the electron configuration can tell me what energy level an electron is in, also which orbital it is in. So we talked about models of the atom, we talked about orbitals, and we talked about the quantum model or the Schrödinger model of the atom. So orbitals, again, are the regions within an atom that encloses where an electron is likely to be. So remember we said that the Bohr model was incorrect, where we don't have electrons orbiting around the nucleus like planets around the sun. Rather, there are orbitals, which is a region three-dimensionally where we might find an electron. So I want to look at an example of an electron configuration, and then we're going to talk about all of the different parts. So let's look at oxygen. Oxygen would have an electron configuration of 1s2, 2s2, 2p4. So first, let's talk about those numbers in pink. Those represent the energy level. So going back to our Bohr diagram, the energy level is the same thing as like the shell or the ring around the nucleus. So this would be my first energy level, which we know can hold a maximum of 2 electrons. This would be my second energy level, n equals 2. So we said electron configuration determines an electron's location. I know that I have 2 electrons in my s orbital in the first energy level. Blue, the letters. This represents the orbital shape. So we're going to talk about that a little bit more in a little bit, and I'll show you what those different orbitals look like, but that tells me the shape of the orbital where the electron is likely to be. Those superscripts in green represents the number of electrons. So looking at this 1s2, it means I have 2 electrons in an s orbital in the first energy level. So I know the shape of the orbital, I know how many electrons there are, and I know in what energy level they are. So I know they're in that first energy level closest to the nucleus. Let's talk a little bit more about those energy levels. So we know that electrons travel in shells based on their energy level. Energy increases as we move away from the nucleus. The energy level corresponds to the elements period on the periodic table. So let's look back at our model on our electron configuration. So if this is oxygen, I would have a total, again, green is the number of electrons, so 6 electrons in my second energy level. 1, 2, 3, 4, 5, 6. We call the electrons in the outermost energy level valence electrons. Oxygen's valence electrons are in the second energy level. So if I were to grab my periodic table and find oxygen, oxygen is in the second period. So this period number corresponds to the energy levels in our electron configuration. Let's talk about those blue letters. Orbitals. The orbitals indicates the electron cloud shape in which an electron travels. There are 4 possible shapes, and the letters that we use to represent those shapes are S, P, D, and F. S would be the lowest energy, F would be the greatest. There can only be one S orbital. There are 3 P orbitals. There are 5 D orbitals and 7 F orbitals. So here's what those orbitals look like. Again, we said we have 1 S orbital, 3 P, 5 D, and 7 F. And it has to do with its rotation around the axis. So S is a sphere. It's always going to look the same regardless of which axis we rotate it around. Here we have P sub X. P they call like a dumbbell or barbell shape. P sub Z and P sub Y. Gets more complicated as we get down to the D and the F orbitals. So again, this is just the shape of the orbital, the region that we are most likely to find that electron. Last part of our electron configuration were those green superscripts, which indicates the number of electrons. So when you are writing electron configurations, we want to make sure that the sum of all the superscripts equals the total number of electrons. The sum of all the superscripts must equal the total number of electrons. So oxygen has an atomic number of 8. That means it has 8 protons. It also should have 8 electrons if it is an atom. So we should be able to count up all of our superscripts, and they need to equal 8. So 2, 4, 8. So that is kind of just an intro to electron configuration. Today we're also going to start looking at orbital filling diagrams. This is just a depiction that represents our electron configurations. you might see boxes. You could also see lines. Either may be used, they both represent an orbital. And we are going to use arrows to represent the electrons. There are 3 important rules to know. First one is called the U2A2 principle. I believe U2A is German for filling up. So this rule has to do with how we fill our orbitals. The U2A principle says electrons must fill lower energy orbitals first. So that means that we need to fill the first energy level with 2 electrons before we can move on to the second. We have to fill that first energy level first before we can start placing electrons in the second energy level. So that is the U2A principle. Electrons must fill lower energy orbitals first. 2 is called Hund's rule. Hund's rule states that all orbitals in an energy level must be filled with 1 electron before electrons can pair. Hund's rule is like the seats on the bus. If you were getting on a bus and there was an empty seat or a seat with someone sitting in it, where would you sit? You would probably sit by yourself, right? So electrons want to do the same thing. If there's already an electron in an orbital, it's going to go into that empty orbital first. 3. This is the Pauli exclusion principle. Which states only 2 electrons can occupy an orbital, and they must have opposite spins. So the way that we represent spin is by the direction the arrow points. So if you have 2 electrons in the same orbital, and again we're using arrows to represent electrons, to represent opposite spins, one has to point up and one has to point down. So let's say I gave you a few diagrams with mistakes. Match the diagram with the rule it violates. So this is my 1s orbital. Remember we said there is only 1s orbital, and the box or the line represents the orbital. So an s orbital only has 1 line. But there are 3 p orbitals. So anytime you draw a p orbital, we need 3 lines. Alright, so take a look at A, B, and C. Pause the video and see if you can, 1, find the mistake, and then 2, match it to the rule that it violates. So hopefully in A, we found a mistake in the 2s orbital. This violates Pauli's exclusion principle. Pauli's exclusion principle says that if we have 2 electrons in an orbital, they must have opposite spins. So these 2 electrons are spinning the same way. So that is my mistake. B, the mistake is in the 2s orbital. This is a violation of the U2A2 principle. So remember, U2A meaning filling up. Electrons must fill lower energy levels first. The 2s orbital is lower energy than 2p. We have to fill 2s before we go on to 2p. In C, the mistake is in the 2p orbital. This violates Hund's rule. All orbitals have to be filled with 1 electron before we compare. So what this one should look like, imagine these are 3 empty seats on the bus. We're going to place the first electron in the first orbital. The next electron is going to go in an empty orbital. Electrons are negatively charged. Like charges repel. Electrons want to be in separate orbitals if they can. So the way this would work for 2p is we would have to put 1 electron in each of the 3 orbitals before we could go back and pair them up. Alright, lastly, let's do one that is correct. Draw an orbital filling diagram. Let's do carbon. So first, we need to know how many electrons there are. So we need to grab our periodic table. If we find carbon, carbon has an atomic number of 6. That means carbon has 6 protons. As an atom, carbon would have 6 electrons. So first, U2A principle, we need to fill lower energy levels first. So we're going to fill the s orbital first. Pauli's exclusion principle, only 2 electrons per orbital, and they must spin in opposite directions. Arrows represent electrons, so far I've placed 2, I have to place 6. Once the 1s is filled, I can go on to the 2s. Again, 2 electrons per orbital spinning in opposite directions. 1, 2, 3, 4, 2 more to place. Once I get to 2p, I need to follow Hund's rule. 1 electron per orbital before they can pair up. Last thing I want to show you really quick, next lecture we're going to talk about how to write electron configurations without drawing the orbital filling diagram. Again, arrows represent the number of electrons. So this would be 1s2. In my 2s orbital, I have 2 electrons, 2s2. In the 2p orbital, I have 2 electrons, 2p2. So we will get to that next lesson.